Okay. Yes, I'm very happy that Michael Ramsey Musolf is our speaker today. Unfortunately, not in 3D, only in 2D, but the talk for sure will be interesting. He's an expert, or one of the world experts on electroweak phase transition, and he will tell something more general, I understand, and then also about his latest work here. Michael, the floor is yours. Please.
Right. Well, thanks very much, everyone, for coming, and Sven and Jose for the hosting and for the opportunity to talk about this topic, which I'm really excited about. And I hope that soon I can be in 3D back in Madrid. And by the way, some of this work had its origins in a program that Sven and I and others co-organized in 2019 in the summer at the IFT. So I'm very grateful. The
pre-pandemic time, yeah.
The pre-pandemic time was very fruitful in Madrid for me. So before I go into the science, because I have all of these institutional affiliations listed, I thought I would take a few minutes just to explain a little bit of that background for people who don't know the story here. My two primary affiliations are at UMass Amherst, and which is in Massachusetts, and the new T.D. Lee Institute at Shanghai Jiao Tong University in Shanghai. And in terms of the science, the focus in these two places is rather distinct. What I'll be talking about today is largely coming out of the Shanghai program, early universe QFT and the phase transition. In Amherst, the focus of the work in my group there is more on low energy fundamental symmetry tests and baryogenesis and electroweak precision. So there's another aspect to this whole setup for me that I think is useful for people to know about. So it's a big global research effort. So why do I make myself so stressed by having all of this stuff to manage? And there's kind of a bigger picture here, which I call this sort of ambassador side. And this goes back to my experience as a PhD student at Princeton. My advisor was Sam Treeman, who's the picture on the lower left. And he worked very closely with T.D. Lee, who's the picture on the lower right, on what is known as the Cuspia program, which was designed to bring students and early career Chinese physicists to the US for training and development of their careers. And it was a very inspiring and very fruitful program. And for me, one way that I honor, the impact that Sam had on my career, as well as this sort of idea, is to try to continue this building connections between scientists, physicists in the West and China, which I think now, given the global situation, becomes all the more important. And so part of my work is really what I call the ambassador side of this situation. And that being said, whatever is going on in the world, I think what connects us is our passion for understanding the fundamental laws of nature. So I summarize, for myself, my motto is, science first, or in Mandarin, 科学第一. And so that's what our goal, that's what connects us. And so that's why I do this. So if you'll indulge me just a little bit more, since you may not have heard about the T.D. Lee Institute, let me just give you a little brief background about it. It was founded in 2016 in Shanghai, because that's where T.D. Lee is from, to honor his great legacy. And it's got really three goals, one of which is to continue this theme of supporting early career scientists. The second is to try to bring the rest of the world and Chinese physics together more closely. And the third, of course, is to do outstanding science. One of the other things that I think is really unique about the T.D. Lee Institute is that, unlike a lot of other research institutes around the world, it has both theory and experiment, and in a big way, and it connects or crosses three subfields: particle and nuclear, astronomy and astrophysics, and quantum science. And we're really trying to be very international. So right now, as you see on the lower right of the slide, about 40% of our faculty members are actually non-Chinese nationals. So that's, I think, quite remarkable already. So I live in the particle and nuclear physics division, and I've shown pictures of we have a lot of early career faculty and not so early career faculty. And you can look at their pictures there, and just for your benefit, there's a few of the research areas that we're focusing on. And in fairness to my other institution, UMass Amherst, where I've been longer, there's a nice center there called the Amherst Center for Fundamental Interactions. And it's also got a great cohort of faculty. And our emphasis there is really on bringing various subfields of physics together across the frontiers, cosmic, high energy, and intensity or precision frontier. And so our focus there has been on doing very focused, targeted workshops, which I think some people already on this at this seminar have participated in. So please keep abreast of that as well. So that background aside, now I want to focus on the science, and let me just tell you what the goals are for this talk. For those who may not have thought about this topic, I want to first motivate the opportunity scientifically associated with the possibility that there was a particular first order electroweak phase transition in beyond the standard model scenarios. And then I want to introduce on the theory side the use of effective field theories in studying the thermal history of electroweak symmetry breaking to address this possibility, illustrate some of the interplay with non-perturbative, meaning lattice calculations, and then highlight some recent results that draw on this interplay, and in particular at the end, the connections between the collider and the gravity wave probes. So key ideas for this talk. The first and really important one is that nature has handed us a scale, which I call the electroweak temperature, and that scale allows this question to become a clear target for beyond the standard model physics for both colliders and gravity wave probes. Unlike many other beyond the standard model issues like flavor physics or even dark matter, where there is such a range that may or may not fall in the purview of our experimental sensitivities. For this topic, I think it really does. The second point is that there's some really simple arguments, almost sort of back of the envelope, that say any BSM physics that changes the thermal history of electroweak symmetry breaking from the standard model history can't be arbitrarily heavy with respect to electroweak temperature or too weakly coupled to the standard model. And finally, to really flesh all this out and provide a robust confrontation of theory and experiment, there's a new era of calculations that need to be pursued, and I'll be talking about that. So the key ideas for this talk are contained in these papers here. I won't belabor them now, but I do want to make a really important couple of acknowledgments. The first is I'm very appreciative of the fact that several people in the audience today have worked on this topic, and I apologize to you for not including references to your work. Simply, it's a lack of time to do an exhaustive referencing in this talk, but it's not because I don't appreciate it. The second is that there are essential collaborators of mine who are earlier career, and I've listed them in this slide here, several of whom are now at the T.D. Lee Institute, and without whose collaboration I would not be able to present this science today. So thank you to them. So the outline is I'm going to start with a bigger picture context and questions, summarize some of these arguments for why the electroweak phase transition is a good collider and gravity wave target, focus a lot on the question of how theoretically robust is our theory in addressing this topic. And then the last maybe 5 to 7 minutes will be on this, what I call the gravitational wave collider inverse problem, and then a brief outlook. So let's start with the context and questions. And so why is the possibility of an electroweak phase transition interesting? From my standpoint, there are 3 answers to that question. The first is, they're listed in the bullets here. The first is with the discovery of the Higgs boson, the nature of the thermal history of electroweak symmetry breaking is front and center. The second and third have to do with implications for the matter-antimatter asymmetry and gravitational wave probes, which I'll come to in a minute. But I want to take a little time on this first bullet because it's the one that gets actually the least attention, I think, in our communities, and I think it's important. So, and I want to do that by analogy to what's been happening in the case of the thermal history of quantum chromodynamics, the study of that in our field. Here is a cartoon of the QCD phase diagram. On the horizontal axis is the baryon chemical potential. On the vertical axis is the temperature. The top part of the diagram is the deconfined phase of QCD, the quark gluon plasma. Down in the lower left is the confined hadron gas phase. And what we have learned from the lattice computations and experiments at the RIC program is that the transition from the deconfined to the confined phase, which occurred in the early universe at essentially zero baryon chemical potential, was a smooth crossover. But there are also strong arguments to believe that if it had been at finite baryon chemical potential, there would be at some point an onset of a first order phase transition in that transition. And there's a critical point where that turns on. And finding that critical point is actually now a subject of the experimental program at RIC through something called the beam energy scan. So the moral of the story is enormous amounts of effort have been put into trying to map out this diagram theoretically and experimentally. So why not do the same with the electroweak theory? That's today's topic. And so to do that, the starting point for many of us has been in perturbation theory, the analysis of the finite temperature effective potential as a function of the Higgs vacuum expectation value, which is shown on the upper left. And what's depicted here are two representative thermal histories of that potential. The far left is a first order history. And in that case, at high temperature, the absolute minimum is at the symmetric phase origin. As the universe cools, a secondary minimum develops away from the origin. And at some temperature called the critical temperature, it becomes degenerate with the symmetric phase. And then as the temperature lowers further, there is a transition to the broken phase. And characteristic of a first order transition is a barrier between these two minima. Now, what one finds in the standard model is that as you increase the mass of the Higgs, which is really tantamount to increasing the Higgs self-coupling, this barrier gets smaller, relatively weaker and weaker and weaker until the transition becomes second order, no barrier. And ultimately, what we find is that the transition is a crossover transition. So on the lower left of this slide is a summary of lattice studies that have identified the maximum mass for the Higgs boson in the standard model for which there would be a first order transition. And you can see that the range is somewhere in the 70 to 80 GeV range. And so clearly we're not in that domain. So if we were to turn that into a phase diagram, in analogy with QCD, it might look like something on the upper right, where in this case, we'll put the Higgs mass on the horizontal axis, the temperature on the vertical axis. This yellow line would be the line for a first order electroweak phase transition from the high temperature symmetric phase to the low temperature Higgs phase. It stops at around 70 to 80 GeV. And over here for 125 GeV Higgs is a smooth crossover transition. So if all we have in nature is the standard model, then in both QCD and the electroweak theory, everything was a crossover. Now, many of us are convinced that for the electroweak sector, at least, that's not the end of the story, that there has to be some new physics at or below the TeV scale. And so in that case, one can ask, how does this phase diagram change? And in particular, is there a strong first order electroweak phase transition? And strong, I'll come to in just a minute. So in thinking about that possibility, I've been quite captivated by something I read in Weinberg's 1974 famous paper on gauge theories at finite temperature. And he laid out how symmetry breaking could be much richer than we're used to thinking about in the standard model. And the example he used there was an ON cross ON setup, not the standard model. And in that setup, there are two Higgses called eta and chi. I'll call them phi1 and phi2. And what he pointed out is that depending on the choice of those Higgs masses at zero temperature, the thermal history of the symmetries in this setup could be quite rich. So just to follow an example, let's take a line that starts with 1. The dot here, open dot, represents the zero temperature Higgs masses. And the line represents the trajectory as temperature is lowered. So at high temperature, you start in the symmetric phase A and then break to a somewhat less symmetric phase called B. That's kind of our usual paradigm. But imagine instead you started in phase C for different choices of zero temperature Higgs's masses, which is a less symmetric phase. As the temperature lowers, actually symmetry can get restored for a while and then break again to a different broken symmetry phase. Or you start in 4, where it's even less symmetric, goes to more symmetric, fully symmetric, less symmetric, etc. So in this really simple setup, there's already quite some richness to what the thermal history could be compared to our, what I call vanilla trajectory one. So in my own case, thinking about how to apply this idea to the standard model, let's imagine a really simple setup where we now have one additional scalar field, which I'll call phi, in addition to the Higgs, and think about how the effective potential and therefore the history of the thermal history of electroweak symmetry breaking could occur in the presence of this new scalar phi. So in this slide, on this axis here is the BSM scalar axis. On this axis here is the Higgs axis. This is how the potential might look today. We have to live over here in the Higgs phase. At high temperature, we would have started at the origin. And the question is, how do we get there? Well, one way is to go directly from the symmetric phase to the Higgs phase in one step. And that transition could be different from a crossover transition due to the presence of this additional scalar. Okay, so that's already interesting. But another possibility, a la Weinberg, might be, well, maybe we go to a different phase first in a multi-step transition to the Higgs phase and ultimately end up in the Higgs phase. So, you know, there's quite a rich array of possibilities here already by just adding one new scalar field to the standard model. So the questions one can ask are, what is the landscape of these potentials and their thermal histories as we extend the standard model? How can one probe this landscape, the finite temperature behavior of this landscape experimentally? And then for theory, how reliably can we compute the thermodynamics? So I think already for bullet one, there's quite a lot of interest. Now for bullets 2 and 3, a little bit more familiar to people, baryogenesis and gravity waves. Let me just remind you that for a first order electroweak phase transition, the way it proceeds is through bubble nucleation. So bubbles of broken electroweak symmetry nucleate in the background of the symmetric phase. And for electroweak baryogenesis, that has to be a sufficiently strong nucleation process. And by the way, we also need new CP violation to get the baryonic symmetry, but the precondition in electroweak baryogenesis is for this bubble nucleation process. And it's also the nucleation and then collision of the bubbles and turbulence and sound waves, et cetera, after the collisions that become sources of gravity waves. And so, and to see either one in reality means the transition has to be not only first order, but sufficiently strong to be defined more detailed a little bit later. So lots of motivation for this question, it seems to me. And so now we can talk about why there's some chance that a combination of theory and experiment might actually determine whether or not there was an alternate thermal history, in particular with a first order phase transition. And for the collider side of things, the two issues that we have to address for collider physics is, what is the mass scale of the new physics? And is that within the reach of colliders? And what are the level of indirect effects, and therefore how precisely does one need to measure properties of standard model particles, in particular the Higgs, to see the effects? And that's what's addressed in this paper here. So let's just talk a little bit more about experimental probes back in our simple setup here. How might we look for evidence and details about this potential? Certainly one way is to make the new particle directly in a collider process, particular probably a PP collision, but could be a click or something like that. A second way is to look for the small changes in Higgs boson properties due to the presence of the new scalar. I call this sort of tickling the Higgs boson due to the presence of interactions with the new Higgs. And so both are going to be very important. And then the third is the astrophysical probe of taking the information we might glean from hopefully an observation of a gravitational wave signal in next generation experiments. So again, for purposes of our discussion, the questions you might ask are, how heavy can phi be? How does it couple to the Higgs? And can it be discovered in a collider experiment coupled with gravitational wave probes? So to think about why there's I think a hopeful prospect for experimentally probing these issues, it's useful to start with a version of the standard model Higgs potential at high temperature. So that's what's shown in the top box here is the high temperature effective potential at leading order in what's called the high temperature effective field theory. And importantly, there are two terms. There's a quadratic terms in the Higgs, h squared, and then the quartic term, self-coupling term, h to the fourth. And for this discussion, the important point about the quadratic term is that it carries a dependence on temperature, T squared, and a temperature quantity called T naught squared. So the formula for T naught squared in perturbation theory at leading order is given in the lower middle red box. And you can see that it's proportional to the Higgs vacuum expectation value squared, but it's not necessarily identically equal to V squared. That relationship depends on the other couplings in the theory, the Higgs self-coupling, the gauge couplings, and importantly, the top quark Yukawa coupling. So depending on what nature had chosen for these couplings, T naught could be close to or not so close to V. Now, it turns out for V being 246 GeV, T naught is actually, quite a distance below that. It's 140 GeV. And so that temperature, I'm going to call the electroweak temperature, and that's what really sets the target for this physics for the experimental accessibility. So let's think about how that gets implemented into questions about precision and mass reach. And again, just to remind you, what's particularly interesting is the possibility of a first order electroweak phase transition where there would be a barrier that separates an earlier phase from the Higgs phase. And let's think about the possible trajectories now of getting to that Higgs phase in the presence of this new scalar, which I'll have coupled to the Higgs through the Higgs portal. So across the bottom of this slide here are three representative thermal histories. And let's start with the one on the lower left. The vertical axis is the phi direction, the horizontal axis is the Higgs direction. The idea here is that the transition to the Higgs phase occurs in a single step at the electroweak temperature. And now if we introduce a Higgs portal interaction, h squared phi squared, with some coefficient I call A2, then at finite temperature, the presence of this interaction can make this transition first order, as we'll see later on, okay? So this is a thermal loop effect. A second possibility is in the middle. This would be a two-step transition to the Higgs phase, where the first step goes actually to the phi phase, and then at the electroweak temperature, we go to the Higgs phase. And in this case, the same interaction can generate a barrier between the phi phase and the Higgs phase at zero temperature, and then the quadratic temperature dependence of the thermal potential turns on and off the transition from the phi to the Higgs phase. So it's a tree-level barrier, a zero temperature barrier, but its effect is enacted due to the temperature dependence of the other terms in the potential. A third possibility is on the lower right, which is a single-step transition now to a mixed VEV phase at the electroweak temperature. And here, the interesting operator, if the gauge symmetries allow it, is an h squared phi interaction that can create a barrier between the symmetric phase and the broken phase. And as in the middle case, this gets turned on and off due to the other temperature dependencies in the potential. So it turns out that for the first two cases, there are some really simple arguments, which I won't go through here because of the time, but encourage you to read in the paper, that imply that for either of these to have a first order transition to the Higgs phase, the mass of phi can't be arbitrarily heavy. Somewhere around 700-ish GeV is a kind of upper bound. And that's really well within the purview of our future collider program. For the third case, the interesting signature here is not so much the mass reach, but with this operator, there is now at zero temperature mixing between the Higgs and the neutral component of the phi. And that mixing will lead to changes in the Higgs boson properties, and therefore precision Higgs studies are a good probe of this effect. And so one can ask, what is the level of mixing that you would expect? And here, we need to invoke these other two considerations, that for baryogenesis, the transition is sufficiently strong to prevent washout of the baryonic symmetry, and the gravitational waves have a strong enough signal. So one can translate those considerations into a rough criteria, which is that, given in the lower left box, that the ratio of the operator coefficient to the Higgs self-coupling times the electroweak temperature has to be greater than of order 1. And it's relatively straightforward to turn that into a lower bound on the mixing angle of about 1%, or if you're interested in Higgs self-couplings, about 0.3%. So this is not 10 to the minus 6 we're talking about. We're talking about something that is in principle within the purview of precision Higgs studies. And what we see in actual real model calculations is these general sort of mass reach and precision benchmarks are quite realized in specific model setups. So speaking of specific model setups, there's been a lot of work over the decades in various BSM scenarios. Here I've taken this nice summary from Jose Mi about different scenarios in which people have pursued, investigated the possibility of electroweak phase transition. And in the paper here, I tried to give as exhaustive a list of references as possible, but here's just to give you an impression that a lot of work has been done. So now I want to raise the question, why should you believe any of it? Okay, and that goes to this question of theoretical robustness. And here I'm going to draw on primarily 3 papers in the last couple of years to address this question. So for the models in phenomenology, the question we really need to ask if we're going to confront experiment is how reliable is the theory? And so why is this a worry? I'll come to it in a minute. But the places where this question creeps in is really, it's useful to organize in 2 categories: the thermodynamics of the thermal history and the dynamics. The thermodynamics, for example, what is the phase diagram? And from the thermodynamics, we get the latent heat or something related to it that's an important input for gravitational waves. And then there are the dynamics, the rate of nucleation of the bubbles. Does the transition to the electroweak broken phase actually occur? If so, what is the temperature, the nucleation temperature at which that happens? What is the duration of the transition, which is important for setting the frequency range for gravitational radiation? And then for baryogenesis, what is the rate at which electroweak phaleron transitions occur inside the broken phase? Is that rate quenched enough to preserve a baryon asymmetry? So there are lots of places where the theory has to be done right, and there are reasons to worry. And let me illustrate here with perhaps the most important reason for the thermodynamics why one should worry. This goes under the name of the IR problem or the Linde problem. And let me illustrate with just a simple example of a bosonic loop at non-zero temperature, I of t. And let's suppose it comes with some coupling squared, G squared in front of it, which often happens. At finite temperature for thermodynamics, the integrals we do are actually 3-dimensional integrals. So there's a D3P. There is the Bose distribution function that takes into account the, how probable it is that the bosons are present in the plasma. And then there's going to be some number of bosonic propagators. So let's ask what happens to this integral when we go to the small momentum regime. Importantly, the Bose distribution function can be approximated by the temperature over the mass in that regime. And so if we take that and translate that into the region of the integration, that's the IR region, then we factor out this T over M, and we're left with just a conventional momentum integral. And the coefficient of this integral in this region now becomes the effective expansion parameter. It's G squared times T over M. Now, why is this a worry? Well, let's look at how M can be. For example, the Higgs boson in the standard model, M squared, depends on the Higgs background field, the VEV, with some coupling squared, G squared, and some numerical coefficient, C1. And it also depends on temperature through the second term. So I'll call that M squared of sub T for temperature of phi. And the point is that near a phase transition, phi is going to 0, number 1. And number 2, these coefficients, C1 and C2 in particular, is typically much, much less than 1. And so the denominator in this effective expansion parameter is not necessarily large, even though it might be large away from the phase transition. So that means we don't have good convergence due to these infrared contributions. Now, just to make it a little bit more quantified, let's define an effective expansion parameter, g squared t over m. It turns out from technical point of view, there's a reason to put in a factor of pi. And one can ask, what is the value of G effective? Well, that's been studied in the standard model. And as I said, MT of phi is infrared sensitive near phase transition. And MT of phi can actually be measured in the lattice. And so if we're in the regime where the zero temperature Higgs mass is near the critical Higgs mass for first order phase transition, G effective is order 1. So this is not a small expansion parameter. Okay. And so we really have to be cautious about the use of perturbation theory, at least in certain regimes where this infrared problem will come back to bite us. There's another problem that's probably more familiar to people on this seminar, which has to do with the need for thermal resummations. This is an old and well-known story. Let me just remind you, using the example of the Higgs boson contribution to its thermal mass, which goes like at one loop, t squared lambda over 24. And if one goes to the two loop order, there's a correction that comes with a factor I call zeta, and zeta goes like t squared over m. And as we just saw, t squared over m squared is not necessarily small. So there's no reason to stop at two loop. One should go to three loop, et cetera, et cetera. And there's really a need to resum all these diagrams. And that's known how to do that at one loop through something called the daisy or ring resummation. That's standard lore now in thermal field theory. One of the caveats about it is it's a little bit ad hoc, because where else do you do this? And what if you want to go beyond the one loop with higher precision? As we're going to see shortly, this is where effective field theory is a particularly powerful way to do it more systematically and improvably. So more generally, there are lots of challenges for perturbation theory, which I've listed on the left here. There's the IR problem, thermal resummations. I won't talk about maintaining gauge invariance, maintaining renormalization group invariance at finite temperature. And all of those issues in principle can be solved by carrying out non-perturbative calculations. In particular, this IR problem gets resolved. The challenge is that doing lattice calculations is computationally intensive. And so we seem to be sort of stuck because most people who work on BSM proposals use perturbation theory, which is fraught with all of these issues. So another way to sort of put out what I think is the challenge is that I call this theory meets phenomenology. You know, the most reliable way to do things is non-perturbatively, but it's really impractical to do a broad survey of models and scenarios. The way to do the latter is to use perturbation theory, but certainly due to these issues, the quantitative and it turns out even qualitative reliability of perturbation theory needs to be assessed. So the way forward that we've been taking is to do what's called benchmarking perturbation theory, which is to use non-perturbative calculations in different scenarios to check how the perturbation theory is doing and see if there are certain things we can still use perturbation theory for, but sort of anchor it to what the lattice tells us. And a key ingredient in that program to connect the perturbative and the non-perturbative side is to use effective field theory, and in particular, what's called dimensionally reduced three-dimensional effective field theory at non-zero temperature. So the strategy is really the following. We're going to employ this effective field theory in two regimes. One regime, we're going to consider the new physics to be sufficiently heavy that you can integrate it out in the first step of constructing the effective field theory and reuse or repurpose existing lattice calculations. And the second, which is now the sort of forefront, is to include the new degrees of freedom in explicit Monte Carlo calculations and then benchmark the perturbation theory that way. And I'll show you illustrations of both. Now, I should say that when I say effective field theory, it's actually a plural, effective field theories. And the reason is the following, that depending on which problems we're trying to solve, there are more scales that have to be taken into account. So for example, for the thermodynamics, there's one effective field theory, I'll call it EFT1. In the case of dynamics, when we talk about nucleation, there's a new scale that comes in, the inverse size of the bubbles. And so one has to construct an additional effective field theory, I'll call EFT2. And then if we're going to talk about Sphaleron physics, there's another new scale. And so there should be another effective field theory called EFT3. Now, EFT1 and EFT2 have been developed. EFT3 is still under construction, so I'm not going to say much about that today, but just be aware that one needs to think about multiple effective field theories. So the rubric for this EFT-ness is what's called dimensional reduction, and it relies on, and the EFT part relies on identifying the scales in the problem. So let's, for the EFTs 1 and 2, talk about the scales. They're listed here on the left. There's the scale associated with the non-zero Matsubara modes that go like integer times pi times temperature. There is the scale of the new physics, which can be larger than or smaller than or about the same size as the Matsubara mode scale, which we sometimes call the super heavy scale. There's the scale of the thermal masses in the problem, would go like the coupling times temperature. For nucleation, there's the inverse size of the bubble. And then what is left is particularly near a phase transition, a light thermal mass scale that goes like G squared T. So for EFT1, the green box shows which scales we take into account. And then for EFT2, we have to add the nucleation scale in our EFT construction. So let's sort of diagrammatically or schematically look at how this EFT construction works, which is shown on this slide here. The line goes from the light scale up to the heavy, super heavy scale, the Matsubara scale. And the idea is that we start with the full theory and we integrate out the non-zero Matsubara modes and possibly the BSM degrees of freedom. And we're left with an EFT called L3. Then we integrate out the time-like component of the gauge bosons, and we're left with another that have a mass that goes like GT. We're left with another EFT called L bar 3, which involves the light degrees of freedom. Now, in doing that, there are two steps to how this goes. There's dimensional reduction, and then there's matching that involve loop effects. For dimensional reduction, the idea is pretty simple. We start with our four-dimensional integrals and using the imaginary time formalism, transform them into three-dimensional momentum integrals with the coefficient of temperature, 1 over beta is temperature, and a sum over all the Matsubara modes. And so from here on, since we're in a three-dimensional situation, it's useful to rescale the fields and the couplings with factors of the temperature, which I've shown here on the right. So that's kind of the basic dimensional reduction. And then to take into account these important thermal loop effects, the way we do it is to integrate Green's functions at each step in the construction of the EFT. For example, let's take the lower left. Here's the formula for the square of the scalar mass at 3 dimensionals. It's 1 over temperature times the 4-dimensional mass field squared. And then there's a correction due to loops in the self-energy function, pi, actually the derivative of the self-energy function called pi prime. For the couplings, here, for example, is the Higgs portal coupling I introduced earlier called A2, and it goes in the 3-dimensional theory like the temperature times the 4-dimensional coupling. And then there are loop corrections that involve the self-energy functions of the fields and a vertex correction. Okay. So we go through this equation at each step. And an important point that I wanted to make is that in this first step, in integrating out the non-zero Matsubara modes, this systematically implements this daisy resummation. And therefore, depending on the loop order one works to, one can systematically improve it in a way that's much more straightforward, I think, than trying to do it by hand in the sort of conventional setup. So that's already kind of a nice feature. At the end of the day, we're going to be left with, in the case where we integrate out the new physics, a theory that looks very much like the standard model only. Here is the potential. It has a quadratic and a quartic term in the Higgs field with 3-dimensional mass squared and couplings, mu bar and lambda bar 3. And this theory has actually been simulated on the lattice in the 90s. So the idea is that when the full theory contains beyond the standard model interactions, the values of these parameters can be what they need to be at finite temperature to have a first order phase transition, but also accommodate the zero temperature Higgs mass that we see today, which you cannot do in the standard model only. And I'll show an example of how that works shortly. So we're going to repurpose in the first setup here existing lattice results for this light theory to infer back about the parameters of the full theory that would need to be chosen to have a first order phase transition. And so let me just summarize the logic. So we're going to assume in this incarnation that the BSM fields are sufficiently heavy or super heavy that we integrate them out in either of these first two steps. We'll be left with an effective standard model-like theory where the parameters are functions of the BSM parameters. And we're going to use these existing lattice calculations to infer back to what those parameters have to be in the region where the lattice tells us this theory would have a first order phase transition. Let me illustrate that with a really simple extension of the standard model that involves adding a real Electroweak triplet, scalar triplet to the standard model. So the triplet has no QCD quantum numbers. It's a triplet under SU2. It has no hypercharge. And now when we think about the thermal potential by adding the scalar, we go back to these pictures I was showing you before. We have two directions in field space, the Higgs direction and the triplet direction. We want to know how this potential energy is going to evolve with temperature, depending on the choice of the parameters. And there are both thermal loop effects and tree level barrier effects that can be introduced when we have this Higgs portal interaction that I mentioned earlier, h squared phi squared. So one possibility, as I said earlier, is to have a one-step transition that is a first-order transition due to new thermal loop effects. Another possibility is to have two steps to the Higgs phase, and in both steps, electroweak symmetry is broken. And so that opens up some interesting baryogenesis possibilities, which again, I don't have time to talk about today. So just in terms of cartoons, it's these two possibilities I alluded to before. So let me now illustrate the use of this EFT plus lattice to see what we learn about the one-step scenario. And why this can give a first-order phase transition is really simple to see. In the upper box is the potential as a function of the Higgs field, doublet, and the triplet. And here is the Higgs portal interaction. The lower box gives the three-dimensional Higgs self-coupling, which is temperature times the four-dimensional self-coupling. Capital lambda is the normalization scale, And then there are these matching contributions due to the loops. And importantly, there's a contribution from the Higgs portal coupling here that comes in squared. And if you kind of go back to the line before, you can see that the overall sign is negative. So it's a negative times a positive number. And so that means that when A2 is non-zero, the finite temperature lambda 3 in the light theory is smaller than it would be in the standard model. And therefore, if A2 is large enough, in principle, there can be a first order phase transition. Now, what we were able to do is to translate these ideas into a phase diagram for this theory. So here's the phase diagram. On the horizontal axis, it turns out it was convenient to choose the triplet mass. On the vertical axis is the Higgs portal coupling. The gray region I'm going to come back to in a little bit later. The light blue region is the region for a crossover transition. The light green region is a first order phase transition. The dark green region is where the effective field theory starts to break down. And the first important point I want to make is that this boundary between the light blue and the green is not accessible with perturbation theory alone. It's only through the lattice that we know where the crossover to first order boundary lies. And so that's a qualitative shortcoming of perturbation theories. We can't get that information from it. Now, on the phenomenology side, there's already some interesting things we can do with this phase diagram. And that's where these dashed lines come in. The dashed lines are the relative change in the Higgs to diphoton decay rate in the presence of the new scalar, the triplet. And the reason why this happens is that the neutral triplet that's important for the phase transition has charged partners that through loops modify the diphoton decay rate, and the same coupling that affects the phase transition affects the diphoton decay rate. So the loops depend on the coupling and the mass, and that's why you get these curves that show different, it turns out, reductions in the Higgs to diphoton decay rate. So one might then say, well, we can add some mass information. For example, disappearing charge track searches might teach us about the mass. And so depending on the outcome of these measurements, you might learn, for example, if the mass were 280 GeV and there was a 10% reduction in the Higgs to diphoton decay rate, you would be in this first order phase transition region. Whereas if the reduction in the Higgs diphoton decay rate were less significant, you would be in the crossover region. So I think it's a really nice illustration of the interplay of EFT, lattice, and phenomenology that we can use to learn about the phase diagram in this BSM setup. Now I want to talk about the case where we actually include the triplet in dynamical situations, which is important if we want to talk about a two-step transition where the triplet itself can get a vacuum expectation value in the early universe. The light theory now contains the triplet explicitly. The one-step first-order phase transition can still occur because of the effect I talked about before on the light theory self-coupling. But now there's an interesting possibility of a two-step transition. And so now I'm going to illustrate what we learned from EFT and non-perturbative calculations about that. And that's this middle scenario here. So here's the full phase diagram. The axes are the same. The colors are different. I'm sorry. Now, what are these different regions? The dark blue is where the electroweak minimum is unstable. So we don't want to live there. The pink region, or the light red region, is the crossover transition that I showed you before. Now, in full confidence, the red region is the one-step first-order phase transition. So in the legend down here, you can see we go from the symmetric phase O to the phi phase in one step through a first-order phase transition. The slice of different colors here where my cursor is the region for two-step transitions, first to the triplet phase and then to the phi phase. For what we learned from the lattice is the nature of those transitions. In the orange region, the transition to the triplet phase is crossover, and in the blue region, the transition to the triplet phase is first order, and in both cases, the transition to the Higgs phase is first order. What these crosses are the lattice benchmarking calculations that we did to find out what the nature of those transitions were, okay? So EFT kind of helps us map out this parameter space, and then we benchmark at various selected points within this parameter space to understand in detail the nature of the phase diagram. Okay. How we determine second order versus a crossover, that has to do with something called susceptibility. I won't talk about that here because I want to emphasize now this slide and then go to the gravitational waves. This slide teaches us something important about the limitations of perturbation theory, even when we use the full power of effective field theory. And let's start on the right. This shows on the horizontal axis the temperature, and on the vertical axis what's called the condensate divided by temperature. So phi squared is for the Higgs, sigma squared is for the triplet. The lattice values as a function of temperature are given by these dots. And the perturbative calculation in the effective field theory are given by the solid lines. Now, what we see is that from the lattice, there are discontinuities in the condensates at certain temperatures. So in this first one, as the temperature is lowered, there is a jump to from a zero to a non-zero triplet condensate, which means there was a first order transition. And then at a lower temperature, it drops back down effectively to zero, and the doublet jumps up. So that's a first order transition to the Higgs phase. So that's a two-step first order history. And that's at least qualitatively reproduced by perturbation theory, although the temperatures at which it occurs in perturbation theory are not accurate. And that's already important for gravitational waves because the temperature comes into the latent heat contribution to the fourth power. And so a small error in temperature, this is not so small, becomes amplified. On the other hand, the slope of these curves seems to reproduce what we get from the lattice pretty well. So we've used now lattice to benchmark, and we would just think to use perturbation theory to shift where these curves do their jumps. But now let's go over to the right. It's the same thing for different choices of parameters, but now for the triplet, the jump is not a jump, a discontinuous jump. It's a smooth rise. This is a crossover transition. So there's no actual phase transition there. Whereas you can see in perturbation theory, we still have a discontinuity. So perturbation theory would mislead us into thinking that there was a first order phase transition in the first step when there actually was not. Okay, so this is just all part of the cautionary tale of why we must include non-perturbative information when we're mapping out the model parameter space and its thermal history, because we can get not only the quantitative information incorrect, but even the qualitative determination incorrect. So that being said, I now want to take what we've learned into this example of applying it to phenomenology of colliders and gravitational waves. And we're calling this the gravity wave collider or gravitational wave collider inverse problem, which you might phrase in the following way. How can a combination of collider and gravitational wave measurements identify a given model or rule it out? And if they identify it, help us determine the parameters in the Lagrangian. Okay, and there are two papers here I'm going to use to start addressing this question. The first one, what we did is we worked with the dimensionally reduced EFT, where the BSM degrees of freedom in general are sufficiently heavy that we get to the standard model like EFT. There's no explicit BSM degree of freedom in the light theory. And what one can do is then ask, where in the parameter space of these two parameters, which I'll say something about in a minute, does one have a first order phase transition? And what are the values of the parameters? Alpha is related to the latent heat of the transition. Beta over H star in effect tells us the duration of the transition. Over on the lower right are the LISA signal to noise curves. So the weakest reach is 1, which is this red curve here. And it turns out that if we live in the 3D standard model like EFT with no explicit dynamical BSM degree of freedom, then we're quite some ways from LISA accessibility. Okay, so LISA is not going to see the signal if we have a first order phase transition in this region, although collider physics might show us that we do. To get to the LISA region really requires looking for the case where the BSM degree of freedom is dynamical, sufficiently light. And so that comes to this second example here, where we now have, from our non-perturbative and EFT studies, the study of the two-step transition, where we keep the triplet explicit in the theory, in the simulations. So let's illustrate how this works now for the phenomenology. Starting with the plot on the upper left, it's the phase diagram again. The horizontal axis is the triplet mass. The vertical axis is the portal coupling. The gray region is electroweak minimum unstable. For the single step first order phase transition, that's this green region here. The light red region is the region where there, from the thermodynamics, would be a two-step history, with the second step being first order. The dotted lines tell us that inside that dotted line region, the second step actually completes. And so that's important for actually having a phase transition. Now, the LISA sensitivity is given by this really thin black line here. And you can see that LISA doesn't tell us a lot about the mass, but it's quite sensitive to the Higgs portal coupling. So imagine there was a LISA observation, then we would learn a lot, but we would still be needing additional information. And that's where the collider information could come in. And that's what's represented by this set of ellipses here, which are the results of a hypothetical set of collider measurements, assuming a certain value of the parameters in the theory. The benchmark A corresponds to assuming a measurement of the mass and the Higgs to diphoton decay rate that I mentioned earlier. So here's this ellipse. And so you can see that if you took the blue ellipse and the LISA line, you would really narrow down the mass and the Higgs portal coupling. If you only had the dark blue, you wouldn't know whether you're in the one-step first order region or the two-step region, whether you were inside or outside the region where the transition completes. And you certainly wouldn't believe you're in this gray region because we can't live here. That's electroweak minimum unstable. So collider by itself in this incarnation would not be sufficient, but collider plus gravity waves would nail it down. Then for some incarnations of the theory, it's possible that the triplet can decay to two bosons. And so, for example, if we did in that case, there was a precision measurement of the decay to two Zs, that's benchmark A prime, which is the light blue region here, and that might provide a self-consistency check on this setup. You know, if the light blue region didn't overlap with LISA, then it would tell us, well, we're not, you know, this model might be realized in nature, but it's not responsible for an observation in LISA. Now, the last thing I want to say before I go to my summary is to ask, is LISA able? LISA doesn't seem to be able to see everything. And so one way to see that is to ask the following question. If there was a measurement from the colliders, what would that tell us about where you would or wouldn't see an observation in gravitational waves? And that's shown on the plot on the right. The dark blue plus light blue is the projection of this blue ellipse into the alpha and beta over H star region. The LISA signal to noise 5 curve is this dotted black line here. And so you can see it covers some portion of that region, but to get the rest of it would need increasingly sensitive gravitational wave probes. And the light blue region, again, is this benchmark point A. So ultimately, a collider measurement may tell us there's a first order phase transition, but to see the direct evidence for it wouldn't necessarily be a slam dunk for the LISA generation experiments. One might definitely need future generation, more sensitive probes. So I think this is a kind of story that I think we need to now investigate more thoroughly in BSM scenarios. So there's been a lot of other recent work on this problem theoretically that I don't have time to talk about here. So I just listed some references, and let me now go to my outlook and conclusions. So hopefully the takeaway message for everyone is that determining the thermal history of electric symmetry breaking is really interesting in its own right from the standpoint of field theory, as well as it's important for baryogenesis and gravity waves. And as I emphasized earlier, the reason why there's some chance that experiment can combine with theory to teach us about thermal histories is the existence of this electroweak temperature that says the new physics can't be arbitrarily heavy or too feebly coupled in general. And that searches for new scalars and precision Higgs studies at the LHC and next generation gravitational wave probes could, I think, conclusively help us determine the nature of the symmetry breaking transition. But we really need to pursue vigorously this program of EFT and non-perturbative calculations to say things robustly. And so I think there's a lot of opportunities for people who are interested to get involved. And with that, I think I'm right on time, and thank everyone for their attention, and we'll stop here.
Yeah, Michael, thanks a lot for this great overview and also some really brand new results. Really very interesting. Are there, well, I see a few applauding. Are there questions for Michael? Well, let me start with a question. I had several, but let me start with one. On slide 76, when you were showing, yeah, exactly. Do I understand you right when you say LISA can see only something in this very thin black line? This is the correct interpretation, yeah?
Yes.
How does it come that the line is so thin? Why does it lose so much sensitivity when you go a little bit up or down?
Well, it's very sensitive to the Higgs portal coupling. I don't have the plot here, but going from where my cursor is here to the bottom is maybe a factor of 10 in the, or a few in the Higgs portal coupling. And you can see that the duration changes by orders of magnitude.
And
so,
why is that?
Well, we don't fully understand the reason why yet. This is now come out of our study of the real triplet, and it turns out there was an earlier study in the singlet extension that showed essentially the same thing, that the Higgs portal coupling seems to be decisive for LISA sensitivity, and the mass, you can vary the mass and you don't get much change. So you can see why it's relatively insensitive to the mass, but very sensitive at any given mass to the value of the Higgs portal coupling.
Well,
that's why
if I change the mass by 10 GeV, which is not much. I mean, the thickness of the line and the dimension of the mass is a few GeV only, no?
Yeah, so
If you
there's
take a
really
horizontal line cutting,
they almost fall on top of each other. In the paper, we have this plot is for a 200 GeV triplet. If you show the one for 150 GeV, it almost lies right on top. So it's really dramatic, right? Which says the gravity wave probe is a great thing if you want to nail down the Higgs portal coupling, because you can do a much better job than even a combination of really precise measurements.
If you see something,
if you see something,
tells me
right?
more that chances to see something in the model are rather slim. This is how I would interpret it.
Right.
Unfortunately,
Yeah. So you might learn from the collider measurements that you lived, say, up here where my cursor is, outside the LISA region, or because of the 95% confidence level, you might, for lower masses, overlap with the LISA region. But if you lived up here, then it would essentially be saying, you're in this region here where LISA doesn't have a sensitivity, you would need a more powerful gravitational wave probe in the future. So we can't give up on the colliders. Not that we were going to, but there's the optimistic point of view, which is, let's imagine something seen, then there's a really powerful thing to do.
This would be great, yeah. But of course, it would be nice, but I think it's not possible to have an argument why we should be living in an area where LISA or the others could see something. But I don't think there's any.
No, there isn't. There isn't, because this value of the Higgs portal coupling, for baryogenesis is not so decisive. Once it's sufficiently strongly first order, and this goes to, we have to study a little bit more this Phaleron transitions in this setup. That might be an argument for why you would live here, but there's no other a priori reason why you would. The thermodynamics tells us a second step of a two-step history that's first order is in this red region here. Then the dynamics tells us we have to lie inside the dotted black line to have a transition that actually completes. And then you can project that region back into the plane on the right, which we do in the paper, and you can see it's still this very thin band that follows this sort of trajectory, and some portion of it lies inside the signal noise 5, but a lot of it doesn't.
Okay, thanks a lot. There is one question. Yeah, Olaya, go ahead.
Hi, Michael. Thank you so much for the talk. It was really nice.
Thank you.
I wanted to ask you if there is any clear or general regime where perturbation theory works for this kind of calculations. Let's say, for example, the high temperature regime, or it really depends on the model that you are studying.
Well, it's a great question. And then we have to ask so first, I think there are two answers to your question. First is we have to define what it means by works. Right? So the first thing is it should get the qualitative features right. So in the setup on the right, it gets the fact that we have two first order transitions, and it's a function of the benchmark, the choice of the parameters, that aren't that different from left to right. This is a larger Higgs portal coupling on the right. And so you might expect perturbation theory to do worse, but on the other hand, the barrier from the triplet phase to the Higgs phase is larger at tree level. And so there's maybe a stronger transition. But on the left, the choice of the Higgs portal coupling is not small, it's 1. And here the IR problem really takes over, it seems. Even though you would expect a first order phase transition based on this tree level barrier, you don't have it. And so I think that so far we haven't come up with a sort of a general sort of statement about where this, qualitative breakdown would occur. And then there's the quantitative one, which I don't see any other way around it other than to sort of compare. So we learn in the case on the right that, the qualitative features are correct. There's an error in the temperatures, about, almost 20 GeV for the first step and maybe 10 GeV on the second step. Okay, so we need that information from the lattice. But then the remaining temperature dependence, the slopes in perturbation theory seem to match the slope, and the magnitudes of the condensates are not bad. okay? So I don't see yet a good set of general arguments. There's some lore in the community that if the transition is sufficiently strong, perturbation theory works, but over here on the left, we would have thought it's sufficiently strong and it doesn't work, qualitatively. So it's an open question. That's why I think it's a great question that you ask. And it would be great to find some kind of criteria, but so far, these are early studies. I don't yet see one.
Okay, thank you.
Further questions? Otherwise, I'll come up with another one.
Okay.
Which goes right to the beginning when you were introducing everything. You said, yeah, at high temperature, of course, we live at the origin. Yeah. Who tells you that at high temperature we live at the origin? It could be that symmetry is not restored at high energies. It's possible, no? And
absolutely.
What would be the implications for what you were saying?
So there are, to my knowledge, a couple of papers that have looked at this in the singlet extension. And the singlet extension is a little bit funny that way for the following reason. Because there's no gauge quantum numbers to the singlet, I can always shift the singlet field and put its high temperature minimum at the origin. And so these setups here across the bottom would be generic even for that case, just to do a field redefinition. The issue of whether you're in a broken phase at Electroweak broken phase at high temperature hasn't, I think, really been investigated much, but it would be sort of like this middle setup here, where at some very high temperature, T phi, you land in this phase here. This would be sort of in the Weinberg theory. Maybe at a really high temperature, you're symmetric, or maybe you just start here. And then you would still have this, we got to get to the Higgs phase, and you could still analyze things that way.
I don't say you can't have electroweak phase transition also in this case, yeah, but
right.
Say, okay.
But you might start here for other reasons that I didn't work out in this case. But for the singlet case, you can always just shift, and effectively redefine the field. So it looks like you're starting from the origin. It doesn't matter where you put the origin in that sense.
But in more complicated models, this is not possible.
Not necessarily possible. And I don't know really where that's been investigated. Now, a couple caveats on that. Paul Langecker and his collaborator looked at QED in the symmetry breaking and restoration scenario. And then later on with Mark Wise and others, we looked at QCD in that scenario. Could you have a color breaking phase and then a color restoration, sort of in the Weinberg sort of spirit? So it's possible in QCD, but you kind of have to stand on your head with the BSM scalars to do it and satisfy all the phenomenological constraints. In the case of QCD, the problem is that the couplings are so strong that the T squared term turns on really fast, and so symmetry just gets restored easily because it's it's the SU3 sector. So it's an very interesting question, but I don't think there's yet a general kind of conclusion.
Okay, thanks a lot. There seems to be another question. Yeah. Juan.
From me. Hi, Michael.
Hi.
So I'm curious now. Once you've added another field to the standard model, let it be a singlet or a triplet, you have to understand also what are its own self-couplings, and also how. What's the chance that if you are in the false vacuum, you supercool there? That means you stay there for a few eFalls, you get rid of all the particles. There's no temperature. And the kind of transition that you have is not a thermal phase transition. It's actually a quantum phase transition. It's like what we envisioned with Bosonic many years ago, that you have a preheating being produced through the quantum fluctuation driving the phase transition. And then you can excite the spatterns. You can go all the way to the Electroweak vacuum by producing the right amount of baryons and also a gravitational wave background. So it would be very difficult, actually, from LISA to distinguish between these two outcomes. So how do you see that?
Well, it's a very good point, which in this sort of more generic framework we didn't consider. This is all thermally driven, as you know.
That's what I understood.
And so the way I would think about it, I don't have an exhaustive answer to your question, but let me just go to this now hopefully famous slide here. So I would try to think of the relevant parameter space in analogy with a phase diagram and ask where would collider measurements plus a LISA observation put us? We could play the same game. It wouldn't be the phase diagram in the way that we've done here because it's not a thermal situation.
That's right.
But it would still be the plane of relevant parameters. And you could ask where could we piece together the collider information, direct, indirect, precision, and then gravitational waves to test whether or not they all coincide or not. That's really the moral of this story. So I would play the same game in that case.
But then in your inverse problem, trying to infer from the gravitational wave background, what kind of transition did you have? You would not arrive necessarily at a thermal phase transition because the shape of the gravitational wave background, the slopes, the scale at which it happens, the way it evolves, all of that is very similar to what you would get in a quantum phase transition.
Right. The quantitative question I would ask is, what are the values of the parameters? You know, it might be that in this parameter space, what you talk about lives down here or it lives up here. Right. The real problem would be if there's a lot of overlap with the thermal parameter space. And I don't know that until it's actually worked out. So it's a good question. I just don't know the answer. Okay. And it may be that other you have to do the plot. And it may be some of the other parameters important. You know, there is a dependence on the triplet self-coupling here that we didn't emphasize in the slides here,
what I was asking.
Where you actually, you know, you're stuck in the electroweak unstable minimum because the relative depths of the vacua in the two cases, if this coefficient called B4 is too small. So we chose values where you wouldn't be stuck. And it might be that you would, in your setup, be in that region.
That actually helps.
And that would be interesting. So there is a dependence on this B4, which we just didn't emphasize.
You have a very light sigma field, then definitely you have a chance that you might get stuck in this minimum.
Absolutely.
And then
absolutely. That's one of the problems we were finding in the lattice simulations, is that the transition would never occur. And so we had to find the values of B4 for which you know, it would actually occur.
Yeah, but we don't have to go that far. I mean, it could at the end occur, but nevertheless, you stay there for long enough that you supercool and then you inflate the universe.
Right. And it's a very interesting possibility. So that's one direction I would pursue, is to think about that.
Great. Looking forward to those results. Thank you.
Another problem on the list. Great. Okay.
I won't be able to help you there.
Great question. Thanks.
I don't see any other raised hands. So thanks again, Michael, for the talk. I stop recording now. Where do I do it?